Alright, now we continue with chapter 14, video part 3. I told you it was a heady chapter, so take your time and review the others if you have to. So we left off with looking at tests of significance, and now let's go on a little bit further. What would happen if we repeated the sample or experiment many times? How likely would it be to see the results we saw if the claim of the test were true? In statistics, the more times you do it, the better you can say your results are pretty accurate. Do the data give evidence against the claim? Okay, so this is where we get to hypothesis testing. So this is what hypotheses are. The statement being tested in a statistical test is called the null hypothesis. Null means nothing, right? If you were a null set in mathematics, it was empty. This test is designed to assess the strength of evidence against the null hypothesis. All right, that's the second bullet. The third bullet says, usually the null hypothesis is a statement of no effect or no difference, or it is a statement of equality. When you perform a hypothesis test, we assume that the null hypothesis is true until we have sufficient evidence against it. Let me give you an example. Let's say that I compared this semester's statistics class with last semester's statistics class, but now I'm using videos and I'm using the live scribe, which I didn't have access to in previous classes. So the null hypothesis would say that there is no difference in a student's output when I use videos as the ones I just mentioned. Okay, so there's no difference. That would be the null hypothesis. But you know, as a statistician, I want to see if there is a difference, but I'm going to test that hypothesis. So I'm going to come up with an alternative hypothesis and say there is a difference. Okay, if my null hypothesis is false, then that means there was a difference, and that's what I really hope to find. The statement we're trying to find evidence for is called the alternative hypothesis, H subscript A. Usually the alternative hypothesis is a statement of there is an effect, or there is a difference, or it is a statement of inequality, because that's what you want to see. Many times scientists or researchers want to make sure that they find that what they're doing in a certain case study is actually making a difference. So they state a null hypothesis saying nothing happens within these regions on the confidence interval that we talked about earlier, and then they hope that something did happen. So they hope to prove the null hypothesis to be false. Therefore, the alternative has to be true. So the alternative hypothesis should express the hopes or suspicions we bring to the data. It is cheating to first look at the data and then frame HA to fit what the data show. Okay? So let's see what we do here. Now here's a case study, and I'm going to go to the book because it has a little bit better of a description. This is the Diet Cola example, 14.5. And they say that the sweeteners in Diet Colas usually gradually lose their sweetness over time. They have taste testers who taste and score the cola again after storage. And so what they do is that we have a new cola, and we want to test to see if it does lose its taste. All right, so here's the new cola and the sweetness taste, 2.0, 0.4, so on. Most are positive. That means they found a loss of sweetness. But the losses are small, and two tasters thought that the cola gained sweetness in storage. Okay, so again, what we're trying to do is see if our cola doesn't lose sweetness. All right, the average sweetness loss is given by the sample mean. So if you take the mean of these, it's 1.02. So that's the sample mean. Remember that X bar. Are these good evidence that the cola has lost sweetness? How do we know this is good? How do we know this is significant? So that's why we do a hypothesis here. Okay, so we make a claim. We make a claim and ask if the data gives evidence against it. Okay, we say that our cola is no different from the others, but if that means that we don't want to, but we really want to see if it doesn't lose its sweetness. Okay, so we seek evidence that there is a sweetness loss. So the claim we test is that there is not a loss. That's what we really want to find out. Okay, so first bullet, if the claim that mu is 0 is true, the sampling of X bar from 10 tasters is normal. Okay, that means the mu is 0. It's normal. All right, that means that the population mu is 0. The standard deviation would be 0.316. Okay, so let's look at what 0.316 looks like. Okay, right here. All right, so remember that as we go back up here. So for cola already on the market, 10 tasters had a mean loss of 0.3. Okay, it is clear from that that from figure 4 to 0.3 is over here, and we had a 0.316. Okay, so these little decimals really make a big difference here. So what we find here in the second bullet, it is clear from figure 14.5 that x bar this large could easily occur just by chance when the population mean is 0. That 10 tasters found x to be 0.3 is not evidence that this cola loses sweetness. Okay, there's no evidence. It falls within. Alright, the taste test for the new cola produced an x bar of 1.02. That's way out in the normal, because here's 1.02. Okay, so far out that an observed value this large would rarely occur just by chance. Okay, so this observed value is good evidence that the true mu is in fact greater than 0. So the true mu is greater than 0. That is that the cola lost sweetness. Way out here. That means that it's too far out. So that means the manufacturer must reformulate the cola and try again. Okay, so that's kind of can be kind of complicated here. So that's all what this says. So I'm going to try to find just a simpler example here in a couple of minutes. But here's how we write this. The null hypothesis is that the mu equals mu of the null hypothesis. Okay, the mu, that's the population, will equal our finding. One-sided alternatives, and we'll talk about that in a couple of minutes as well. And two-sided alternatives look like that. So you might have seen something like this in research papers that you recently did. Okay, so let me show you. No, not that. Let me show you if I can find it. There it is right there. Okay, here's some examples. One-tailed upper tail. Okay, that means, what does that mean? Let's go back to the, one tail means right here, upper tail. Okay, that's what it means. So remember that here. So we have an insurance company. It's reviewing its current policy rates. When originally setting the rates, they believed that the average claim was $1,800. They're concerned that the true mean is actually higher because they could potentially lose a lot of money. They randomly select 40 claims and calculate a sample mean of $1,950. So assuming the standard deviation of claims is $500, and they set an alpha, okay, that's going to be a 0.05. 0.05. They want to set this as a 0.05. Where do they get that? Remember, 95.95. Let's go back to this right here. Z, critical, 0.95. Okay, at 95%, right there. Okay, remember that, 0.95. So if we do this chart here, 0.95, then we have 0.5 in the tail over here. That's what they mean. So we want to see if the insurance company should. So they set the null and alternative. So the null is that the mu that is going to be less than or equal to 1,800, and the alternative is that it's going to be greater than 1,800. Okay, they want to test that. So they test this. They use this formula here. Where does that come from? Let me show you where it comes from. Right here. So this is called a test statistic. It's in your textbook. It says taking a simple random sample of size n from a normal population with unknown mean, mu, and known standard deviation. There you go. That's that simple, our simple problem that we've had for this chapter. The test statistic for hypotheses about the mean of a normal distribution is the standardized version of x bar. You're going to take x bar and standardize this. This is really the same equation we've been using all the time. But now we're just finding the z score over here. Okay? There's our sample mean. There's our null hypothesis mu. There's the standard deviation of the population and the square root of the number of people that we surveyed. So they use that same equation. So let's look at it. So they found the $1,950 right there. That's what they found from the 40 claims. Okay? The mu is 1,800. That's what they said. The mu should be 1,800. That's a null hypothesis. They want to see if 1,950 is really significantly greater than 1,800. Then they take the standard deviation of the population and divide by the square root of 40 people that they surveyed. They come out with a 1.897. Okay, a 1.897. Now remember z, they set it at 0.05 on one side. Well, if we look at this, 0.05 is 0.95 over there. That means that 0.95, 95%, 0.95 is a 1.96. So they're testing the 1.96. So this is what they did. They found 1.897 and set the rejection region. Looking at the picture below, here's the picture below. Okay, there's a 1.96 right there. Remember, 95% all the way over here. Well, that leftover tail is 0.05. So looking at the picture, we need to put all of the alpha in the right tail, 1.96. We got a 1.897 right here. Okay, here's the 1.897. Take that number and you put it right there. Okay, and what you can conclude is that since the 1.897 is less than our region, our test statistic is not in the rejection region. If it would have been here, we could have rejected the null hypothesis. Therefore, we failed to reject the null hypothesis. Therefore, we cannot conclude anything statistically significant from this test. It cannot tell the insurance company whether or not they should be concerned about their current policies. Okay? It didn't test anything. Alright? It wasn't significant to make a rejection of the null hypothesis. So that's a one-tail test. Now, it's a one-tail test, lower tail. Okay? We're going to look at the tail on this side, over here. So we want to go on that side. Sometimes you want to test to see if it's higher or lower than your population mean. So we're trying to encourage people to stop driving to campus. The university claims that on average it takes people 30 minutes to find a parking space on campus. Sounds like the USM campus down in Gorham in Portland. I don't think it takes so long to find a spot. In fact, I have a sample of the last 5 times I drove to campus. I calculated my time to be 20. So my sample is 20 out of 5 times. Assuming that the time it takes to find a parking spot is normal, a normal curve. That's what it means, normal curve. Then the standard deviation is 6 minutes. Perform a hypothesis test to see if it is significant. And we're going to set it at 0.10, so that's 90%. So that's even sharper, 90% over here, okay? Less region. So if we go to our table, 90% is right there. So the Z down at the bottom, 1.645 would be negative 1.645. It should be, if I'm doing this correctly. So he set the null hypothesis that the mu is going to be greater than 30, less than or greater than 30. I hope that it's less than 30. Okay, so the null hypothesis says that times are going to be equal to or greater than 30 because it won't make a difference. I want to show that my 20 minutes makes a big difference. Calculate the z-score way back here. Z-score, that's what it looks like. Calculate the z-score. By now you should know with these numbers. We get negative 3.727. Negative 3.727. Do you remember I said when you go over here you get a 1.28 for a 90%? Here's our tail. Right here. That's 90% over here to over here. Okay, so tail is 0.10. So if I set it pretty high, then it looks like I'm going to fall right in this region. Okay, because negative 3.727 is in the rejection zone. So we conclude that it is in the rejection zone, therefore we reject the null hypothesis. Ta-da! We can conclude that the mean is significantly less than 30. Thus, I have proven, actually proven is not the best word, supported, or with confidence said that the mean time to find a parking space is less than 30.